Hello, everyone, and welcome to our webinar on the next generation educational kit. Today, talent gap poses a significant challenge for both the RF engineer and the communication engineers. Addressing and fulfilling the industrial demand is a pressing issue. In this webinar, we will show you a new toolkit designed to help you tackle this issue effectively. Enjoy the webinar. Hello, everyone. My name is Ethan Ling, the co-founder and the VP of TMYTEK. This is the agenda for today's webinar. We're going to cover a lot of topics, including 6G. We talk about the issue and challenge, talent cultivation, and what is the solution that will be proposed, hands-on experience, and demo. 6G is coming soon. This is a new era of mobile connectivity. Millimeter wave is still the heart of 6G along with the upper mid-band. Let's have a look over those bands. First, let's look at the mid-band. Ranging from 1 to 6 gigahertz, this is already the backbone of current 5G deployment. They provide wide area communications with advanced MIMO capacity. Moving up, the upper mid-bands spanning from 6 to 24 gigahertz were introduced with 5G Advanced. This band, also called FR3, it offers additional capacity and serving as an alternative to millimeter wave bands. The millimeter wave bands ranging from 24 to 61 gigahertz. This is defined in 5G FR2, providing large bandwidth and introducing sensing capabilities, which is crucial for 6G applications. Lastly, sub-terahertz. This is a extremely high frequency. Research group are very interested in this, but it's not yet been in the mainstream of mobile communications. Together, all these advancements are sharing the future and unprecedented connectivity and innovation. So we believe that millimeter wave is the driving force behind the next generation of innovative applications. This technology not only enhances communication speed, but also unlocks new possibilities for sensing and connectivity. As we embrace this advancement, we are setting the stage for the future applications. Autonomous driving, non-terrestrial communications, remote surgery, defense, logistics, retail, and even AR, VR. Let's review the momentum has been already created since 5G for millimeter wave applications. One of the key applications is fixed wireless access, FWA, which leverages advanced millimeter wave phase array antenna technology to achieve kilometer scale coverage. This development positions a fixed wireless access as the wireless fiber for home connectivity, offering superior performance comparable to traditional fiber optics. Moreover, the use of massive MIMO technology enhances both the FWA and the mobile broadband service, pushing the boundaries of communication range and capacity. Network slicing further allows for differentiated performance and catering to new and advanced use case that is demand high precision and reliability. As we continue to explore transformative potential of millimeter wave technology, let's pay some attention on 6G NTN, or non-terrestrial network. This network promises a more efficient, stable, and seamless connectivity, building on the momentum established by 5G millimeter wave. So as you can find, there's a lot of hot topics on software-defined satellites or reconfigurable ESA, which is electronic steering array antenna, are becoming mainstream, enabling dynamic adaptability to different orbit. High-altitude platform stations, or HAPS, is getting more popular as a solution served between satellite and the ground sector. Those innovations are propelling us into a future where seamless high-performance connectivity is a reality for everyone, everywhere. Before diving into the solution, it's crucial to understand how important of talent cultivation in leading tomorrow's innovation. According to the U.S. Bureau of Labor Statistics, between 2016 and 2024, the tech industry is projected to face a shortage of 6 million engineers. This talent gap presents both a challenge and an opportunity. It's a call to action for us to invest in education and training that will equip the next generation engineer with the skill needed for future wireless communications. Let's look at the challenges in teaching. First, the complexity of the subject, like a signal processing to array antenna and beamforming, coupled with the lack of practical teaching set and the high cost of millimeter wave hardware, presents obstacles for both educators and the learner. So at TMYTEK, we're excited to introduce the NextGen wireless education kit to resolve the issues that's raised. This practical toolkit is crafted to help educators and students to explore and understand millimeter wave technology in depth. This solution includes a full source set of hardware, software, and cutting-edge courseware tailored for 5G, 6G, and even non-terrestrial networks, NTN. Our goal is to democratize the access to millimeter wave technology by providing affordable hardware that makes learning both accessible and engaging. The NextGen Wireless Education Kit empowers not only educators to keep pace with the latest technology, like a 5G, 6G, or for future technologies. It is also equips the student with the skill needed for future. With a toolkit like a millimeter wave, dev kit, and the UD kit, now it's time to delve into the solution. NextGen Wireless Education Solution. There are two kits, millimeter wave dev kit and the UD kit. As you can see, black box and a white box. The millimeter wave dev kit is equipped with 5G FR2 beamformer, a patch array antenna, a 28 GHz continuous wave source, and a power detector. These components are essential for hands-on learning in millimeter wave technology, beamforming, and so on. Complementing to this is the UD kit. UD stands for up-down converter. So this UD kit includes two up-down converters along with a signal generator, plays the role as LO, local oscillator. This kit provides a comprehensive platform for educators and students to engage with cutting-edge wireless technologies in a practical and accessible way. The NextGen wireless education solution includes hardware, software, and courseware. Let's start with the hardware. Our array antenna kit operates at 28 GHz, and it includes a beamformer with a 6-bit phase shifter, an amplifier covering from 20 to 40 GHz with a 15 dB gain, and a signal source ranging from 26.5 to 29.5 GHz, and a power detector spanning from 0.1 to up to 40 GHz. Additionally, we provide frequency converters along with a signal generator, all are crucial for hands-on understanding of how millimeter wave works. On the software side, we provide a GUI along with the API. The GUI is a very intuitive user interface for you to control the devices. The API is compatible with multiple engineering languages that we are going to introduce later. On the courseware side, we offer two options. The first one is Millimeter Wave 101. It covers essential topics like link budget, interference, beamforming, and many so on. For those who are interested in non-terrestrial network, for NTN and IoT communications, we offer this optional module on BCH and LDPC encoding, DVB-S2 channel, receiver simulation, and network. This comprehensive package not only provides the tools necessary for theoretical learning, but also emphasizes the practical applications, preparing for the students to handle the real-world challenges in wireless technology. Here is a hardware list with the photos. As you can see, that we create the devices. It looks really nice and easy to use. Our millimeter wave beamformer GUI, we call it TMX Lab Kit, an intuitive interface for controlling the phase and the amplitude of each RF port. It enables precise beamforming capability. This GUI connects to B-board through LAN port. Likewise, the GUI also can be used to control the frequencies of UD-Kit. Additionally, our API supports multiple engineering languages such as LabVIEW, Python, C#, C++, and so on. We even offer a demo website to show you how this nice GUI is working. Now, I'm excited to present how we can build a complete wireless testbed by integrating two kits together to create a robust system for hands-on learning and experimental purpose. The system architecture begins with the baseband processing, which is facilitated by software-defined radio, SDR. So NI USRP can be an excellent option for this. This is a foundation where digital signal processing takes place, allowing for flexibility and adaptability in various wireless communication scenarios. It's programmable. Next, we have an up-down converter, which up-convert the baseband signal to RF. So this component is connected to the UD board, ensure efficient signal processing and management in millimeter wave band. The RF front-end part is the heart of our testbed, consisting of B-board. In receiver side, we have Coco antenna along with the amplifier. So this setup is designed to handle millimeter wave RF signal, providing amplification and directional transmission capabilities. As you can see, there is a shared local oscillator is used to maintain synchronization across TX and RX. And so this shared resource is crucial for coherent signal processing and transmission. On the receiver end, there is a down converter translate the high frequency back to the baseband. So the signal will be further processed by the SDR. It's time to get hands-on experience. Our NextGen education kit offers a comprehensive courseware, including two parts, Beamforming 101 and the NTN IoT communications, which is an optional module. In Beamforming 101, we cover the basic of RF theory, including link budget, channel gain, interference in either conductive or in radiation method, OTA. We cover the theory behind beamforming and the beam steering. We also educate students how to measure beam pattern. In NTN optional module, this courseware covers encoding, modulation, channel simulation, DVB-S2, and so on. And welcome to Beamforming 101, a crucial component of our NextGen education kit, which is we designed to provide a solid foundation in RF. In today's high-frequency communication landscape, understanding beamforming is essential, especially as we move toward 5GFR2 millimeter wave bands, where array antenna plays an important role in overcome the path loss. This course begins with the basic of RF knowledge, covering link budget, calibration, and gain measurement. These fundamentals are super important for students to grasp the complexity of beamforming and beam steering. So students can engage in experiment to explore the theory and how the beam can be measured. So it is also important for students to understand the interference of EM wave. So either constructive or destructive interference experience in either conductive or OTA method. Of course, beamforming and the beam steering. We also offer receiver gain and the phase alignment and so on. So in this beamforming 101, students can definitely learn a lot. Let me give you an example that I captured from the lab number 5 from the courseware. So this lab is about a beamforming and the beam steering. The objective of this lab is to help students to grasp the beam steering and to study the fundamental principle and the equations behind. Then after that, the students can decide their own beam pattern, and so they can steer the beam on their own. We offer a step-by-step guideline so students can follow and see how it works, what should be expected. The student can synthesize the beam by putting the calculated phases difference to each element, each antenna element, and then measured it. So all this happens with a very affordable hardware, including beamformer, array antenna, power detector, and omnidirectional antenna, and the fixture amplifier. So this really will offer a great learning kit for the students. So let me give a quick example. In this example, originally we emit the beam in 0 degree, which is a bore side, and we take a measure over the power. So we measure minus 11 something in this bore side, and then we steer the beam. Now we rotate the device physically to somewhere. For example, this 30 degree, but we take another measurement. All right, so now the power is down to minus 17, almost 18. Students can decide the beam pattern to steer the beam back to bore side. All right, so after the students applying the phase differences, again, minus 11 dBm is observed. So that really gives students a good way, a very intuitive way to get a hands-on experience, right? Let's explore the theory behind beamforming that a student can learn. So focusing on the relationship between array antenna theory and the beam direction. Using this NextGen education kit, the student can calculate the phase difference and to synthesize beams, understanding how parameters like the angle, beam angle, and distance between the antenna elements influence beam direction, and effectively to decide the right beam to overcome the beam steering problem issues that I showed in previous slides. So let's look into this optional courseware module, the NTN IoT. So in this course, we like to offer the principle of encoding and modulation in modern communication system. Our course leverage MATLAB-based labs to teach students about the BCH and LDPC encoding, crucial for advancing global connectivity through 6G NTN-based satellite communication. This next-generation technology aims to diffuse network and enhance the worldwide communication capabilities. So we will dive into the basic principle of modulation scheme. For example, it's 16 APSK by using MATLAB. Additional, students will learn about the principle of DVB-S2 waveform. They will have the experience to see how to use USRP to generate the DVB-S2 waveform and set up an end-to-end experiments with the NextGen wireless education kit to explore the application of DVB-S2, a real millimeter wave frequencies. Interference management is another key topic where students will simulate interference using MATLAB and talk about strategies like the multicolor frequency reuse and the pre-coding techniques to manage interference. These skills are essential for optimizing satellite communication network. The course also covers technologies to be explored for 6G NTN, including satellite communication standard, Earth to space, or even intersatellite communications, and the communication payload technologies such as an antenna, phased array technology, and so on. So by understanding these components, students will gain insight into a typical satellite communication network architecture, including satellite internet system, the core network, G-Node B, and so on. So let's delve into the setup for this NTN end-to-end connectivity experience. Our platform features a DVB end-to-end semi-physical communication system that supports or encoding and decoding mode in DVB-S2. This setup enables real-time signal processing, including modulation, demodulation, encoding, decoding, and synchronization, and so on, ensuring comprehensive learning and experience. And this DVB-S2 transmitter technology support various modulation schemes, such as BBSK, QBSK, APSK, 16 APSK, and so on. The students can perform real-time measurement of modulation, EVM, error vector magnitude in physical layer. So even they can have the experience on bit error rate or a link of the block error rate in either physical layer and the link layer, compliant with the DVB-S2 standard. Moreover, the system is customized for secondary development, providing students with a flexible and robust platform for innovation. All right. So let me give you an example that I captured from the lab number 9 for this optional module. The students will engage with this end-to-end DVB-S2 testbed set up along with USRP and our NextGen education kit. So this involves the processor for both the transmitter and the receiver. All right. So whenever there are two MAP programs to process, one for TX, one for RX. So whenever we align both TX and RX, we are able to see the spectrum and the constellation diagram can be seen clearly from the application. As a key component of this setup, it's about a USRP. So USRP receives a DVB-S2 signal and transmits them, converting baseband signal to low-band RF, so that our low-band RF can be up-converted into millimeter waveband with our NextGen education kit. This provides a flexibility in bridging software simulation to the real-world application. So all the setup here are super important to offer students with the necessary hands-on experience. Now you understand how next generation education kit work with the courseware. You already obtained some hands-on experience. Now I'd love to share further with you. With this kit, it's not only about these two courses. We can explore more for the future technologies with the kit. Now let's look at the 6G ISAC or JCAS, which stands for Joint Communication and Sensing or Integrated Sensing and Communication. They refer to the same thing. This technology is pivotal for 6G as it combines communications with environmental sensing, allowing for both data transmission and environmental data collection through a shared infrastructure. So when we talk about integrated integration in ISAC, that implies a different level of integration, such as sharing sites, we share spectrum, or even we can share hardware. Ultimately, we like to reuse waveform and the signal. These integrations enhance efficiency and the functionality. The 3GPP technical reports outline about up to 32 ISAC use case, including for unmanned aerial vehicle UAVs. In this scenario, covers transportation, automotive, industrial, logistic, and mobile network performance. This application highlight the versatility and the potential of JCAS or ISAC in various sectors. So our work with the GNU Radio and NextGen wireless education kit demonstrate the practical applications for radar. So there's a lot of potential applications for radar sensing, to measure the range, velocity, and the direction. Also to detect the motion, or even the radar can be used for collision avoidance, vital signal detection, and many so on. So through these advancements, ISAC technology really promised to revolutionize how we perceive and interact with the environment. Our hardware, along with Google Radio, radar sensing application, you will see this in demo section. It's really interesting demo, and we believe this can offer students and extra value in addition to the two courseware we just introduced. In TMYTEK, the innovation never stops. We're going to roll out a solution for smart deployment, reconfigurable intelligence service, RIS. This 5G in our FR1 and FR2 coverage solution is optimized for R&D, for field trials, and prototyping. And now we believe that this solution, the combination of the RIS and the NextGen education kit, will offer extreme values to the students. The students can learn how to optimize wireless signal propagation in smart city, for example. They also can have the hands-on experience, how to dynamically adjust the reflection angle to create hot zones or cold zones. You will have a chance to solve the non-line of sight challenges introduced in millimeter wave communications, enhance signal coverage for 5G and 6G deployments. Now let's highlight a success story from Longhua University, where advanced RF training and the wireless communication courses are implemented and transform the education for teachers. This program addresses extensive millimeter wave hardware challenges and provides a detailed lab sheet supporting a wide range of wireless communication experiments. The university are increasingly adopting this solution. With this success story from Longhua University in Taiwan and integrating it into their 5G curriculums. So this enables practical learning experience in beamforming, beam tracking, which is crucial for modern communication technologies. So despite challenges like limited teaching material and expensive 5G equipment, this hands-on approach aligns with Generation Z's preference for experimental learning and making theoretical classes more impactful. So we hope that the kit helps you. Thank you for your attention. So don't go away. We're going to have a demo section along with a testimonial from UK. Thank you.
Hello everyone, I'm Rona Saad from the University of Sheffield, a current user of TMYTEK. So I just want to demonstrate in a couple of minutes why we have a kit, how it's got to reduce us in the University of Sheffield. So we first take here as a test bed, basically to use for educational and research purposes. It really serves as a very good tool for us to experiment with designs we make and to try to look at the system from a transceiver point of view in frequencies as a millimeter wave, such as 28 gigahertz of learning with part education and research. But currently, the kit is set up as a beamformer working at 28 gigahertz. It's a 1x4 array with 4 channels, transmitting from this end and receiving from this end. So currently, with our proper line of sight, we can see that the power level is around -9 dBm, which is obviously, if we move the beam away, we can see a drop of signal level to -23 dBm. So as in Sheffield, we are quite involved in 5G, 6G technology with our 5G millimeter wave facility and a new 6G system that we have installed. We are really interested into educating our students and researchers in technologies at millimeter wave frequencies. So with this first bed as it's on, students have been using it to understand the beamforming and how the antenna array is basically developed to form a beam and how it transmit and receive work. In addition, we part some projects going into the design of the array itself and recently some of the reflective intelligent surfaces. So these are some prototypes has been designed to be tested with the development kit itself. So I'll just show you a demonstration of two examples. So currently the beamformer is set within line of sight at 28 gigahertz. So if I use this surface, which is supposed to be more of a transmit array, so I put this between the transmit beamformers and the receiver. You can see the signal level almost doesn't drop. It stays between -9 and -10 dB because this type of surface is a transmit array. Okay? Now, if I replace this surface with the equivalent of a band stop filter or a reflector array and place this surface designed at around 28 gigahertz, you can see within the line of sight, I can still see that the signal has dropped from -10 to -30 dB. So the TMYTEK kit has been extremely useful on its own as a test bed to design and sell some prototypes that we make at Schleffen. So it's really of good use for us as a moment. Thank you.
Hi there, this is Sean, and Field Application Engineer from TMYTEK. Today we are going to demonstrate about NextGen, which can be upgraded to support millimeter wave communications and used for educating the next generation in millimeter wave technology with various software interfaces and principles. So let's get started. We use NextGen to conduct a simple beamforming experience to demonstrate our hardware setup. We have an SDR to connect it to our computer for baseband signal generation. And NextGen LO provides to two UD boards and SDR for the missing. Then, transmission and reception are carried out through the B board and the COCO antenna. We use the LabVIEW software to configure our SDR for the transmitting and receiving signal, provide the IF signal, and we only have to adjust the outputs, the IF signal, the power, and the desired number of QAM to establish communication. The signal constellation, it shows a signal performance in the results. By using our GUI to control the B-board and adjusting the parameters of phase in different channels, we achieve the constructive and the destructive interference as mentioned in the lab sheet, ultimately achieving the beamforming control. Here, we adjust the beam steer to 30 degrees, and you can observe a significant decreases in the quality of the transmitted signal. When the signal is moved back to the 0 degree, and attempting to restore the communication, the signal quality improves once again. In this second demo, we use the NextGen to interface with the GNU Radio, the open source software interface for the radar applications. We utilize the SDR for baseband generation and control of the CW radar signal, and use the LO as the signal source for the UD board, and mixing with the SDR radar signal. Then we utilize UD boards for signal mixing and transmission through the B board, while the processing the signal receives signal with filter module along with the COCO antenna. The ultimate goal was to evaluate Doppler shift performance and display the process shift signal on this block, and converting the Doppler shift to audio output, displaying the result through the sound card on this block when there is movement of obstacles. the sound will change accordingly, making it an interesting experience that further demonstrates the feasibility of this architecture, supporting the multiple applications from beamforming to radar systems. Alright, have any questions? It's time to kick off the Q&A section.